4.7, this is on variable coefficient equations. This will be the last section we cover in chapter 4. And even so, we're going to cover it somewhat briefly. We're not going to do the general case of anything. We're just going to show the concept and then show a specific special case. So if you have non-constant coefficients, so variable coefficients, you might say you have some function a of a2 of t, y prime, a1 of t, y double prime, y prime, and then a naught of t, y equal to a function f of t. We will assume that the a sub 2 is non-zero. That I said k there. We might be making the assumption that they're all non-zero, which is fine. And that's the case when you look at the derivation as I think about it. All right, so that's true for all t in some interval. All are continuous, so all a's are continuous. First thing you do is like a standard form thing. You divide out by a2, so we were assuming, of course, it's non-zero. And we get the standard form. So the next theorem is the existence and uniqueness solutions, and I'm just going to paste it up there. It's just like the ones we've done before. Okay, so this is the existence and uniqueness. You can copy that down. So so when you have this, here's the general standard form like this. We will assume P of t, Q of t, and G of t are continuous functions on some interval AB. And then for some y0 and y1 in R, there exists a unique solution y of t on AB for this function. And then these are your initial conditions, of course. So here's your t0, y0, and I suppose, oh no, there it is. So t0 is in some interval. So we're not going to go through the proof. This is not in this book. It's in chapter 13, I think they say. Anyway, it's the next level stuff. So we're not going to worry about it. And even so, we are only going to look at a special case. All right. So we will look at, or we will consider a special case called the Cauchy-Euler equation, C-A-U-C-H-Y, Euler equation. So this is definition 2, defining what that is. And it is a very special case. You will see it looks like this. A t squared y double prime of t plus bt y prime of t plus cy equal to f of t. A, B, and C are all reals, are all real constants. And of course, t is your variable. So now you have basically what you're doing then is these match. Double prime, t squared, prime, t to the first. Basically no prime, no coefficient. So that's what you're adding to this, is that t squared and t. So first thing we do is divide out by at squared, and we look at the homogeneous case. All right, so this is what we're going to do. So in standard form, we write y double prime plus b over at y prime plus c over at squared y equal to f of t over at squared. And we have to assume, of course, that t is non-zero. So what we'll do, standard practice here, is just to check out the solution for t greater than 0 and t less than 0. All right. Now when you look at the actual examples, we're actually only going to look at the homogeneous case. All the cases we'll do look at only are those. So we'll derive it and essentially get the auxiliary equation for the homogeneous case. All right, so let's do that. So f of t will be 0 essentially. So let's just derive that, what that looks like. So for the homogeneous case, we're going to let t be greater than 0. So it'll just be our positive cases. And from examples, I will show you how to handle the less than 0. Okay, and y equal t to the r. Well, we're going to let y equals t to the r. Okay, then basically this is how they do it, and they basically know the answer, so we're just going to do it and show you that it works essentially. So if you look at, if y is t to the r, that's essentially going to be the solution, and then you just take the natural log to get r. Anyway, we'll get there. Then y prime, you got to do the derivative of that. So y prime is equal to where'd it go? Then ty prime is equal to tr t to the r minus 1 because we want, where did it go? We want that. All right, so then let's just roll along here. So then we get t squared y double prime equal to, and then you got to do chain rule on that. I keep saying chain rule, product rule on that. Then it's t squared r minus 1, t to the r minus 2. So check that. That's r times r minus 1, t to the r. So now we can substitute into the Cauchy-Euler equation with f of x equal to 0. Okay, so now substitute into the Cauchy, C-A-U-C-H-Y, Euler, whatever, equation with f of x equal to 0. So we're going to look at that. Okay. Okay, so what we get is this. Okay, so f of x equals 0. All right, so now substitute all of those back. So we're taking this, putting it here, and this, which is this, putting it here, etc. So that's what we're going to do. So when you do that, you get this equation that we will simplify. AR, r minus 1, t to the r, plus BR, t to the r, plus CT to the r, equal to, and then, okay, so now I'm not going to show all this. You expand it and recollect it, and you get this form. AR squared plus B minus A R times R plus C, and then that's T to the R equals 0. Okay. From there, since T to the R is non-zero, basically we can write or since we are assuming T is non-zero, or T to the R is non-zero, we have we can divide it out. So once we divide it out, we have this form. This is essentially this is basically our characteristic or auxiliary equation for the homogeneous case of the Cauchy-Euler equation. Okay, so that's the characteristic or aux equation. I think in the book they call it the characteristic. It means the same thing. So I don't know why they changed it right there, but it's the same thing. Okay, so from there, basically we're going to solve that very similar to 4.2 with like the constant coefficient case. So we have three cases. So we have distinct roots, repeated roots, and then complex conjugates. Okay, so there's three. I'll just say I'll move this up. So three cases, just like in 4.2, and we're just going to go over them. So number one, you know what? Let's just do this because it's pretty straightforward. And and then we'll do another video for the examples. Okay, so let me just pull that over here. Okay, so here's all the examples. If I can collect it all in one deal. Sometimes that doesn't work very well. We'll see. Okay, that looks fine. So this is what I was saying. So I was in 4.2 with constant coefficients. We will have three cases. We have two roots of the given. I didn't star that. This guy was starred. So two roots of this. I know in the book they like label it all these different equations 1 through like 9 sometimes. It's kind of ridiculous to follow. So I'm trying to just do it as close as I can with my little star. That's a little more typical for lecture notes. Okay, so those two roots of this that are distinct, then you have these, basically these are your solutions, those two cases. Then you have repeated roots, that's this case. And then these are your two solutions. To solve that, and you can look at the theorem-8 reduction formula. We're not going to go over that. There's just too much stuff to go over. Time to move on after this chapter. And then, of course, the complex roots, complex conjugates. Of course, there'll be conjugates. So you look for your alpha, beta, and then, but now your solution is going to look like this. You have your T alpha, but you have beta, and then you have natural log of T, which is interesting to me just because the cosine of a natural log, that's like very, not that it means any difference, but what's the word? Not irrational, but transcendental. So both of these are, so it's like you have a composite function that are both transcendental. So transcendental functions, whole nother topic, but that's like E and any trig functions, stuff that's not polynomials and rational functions are transcendental. A natural log, obviously. Okay, so when when I ask you this or it comes across, I mean you'll be able to look everything up and do it just like the rest of them, but kind of skipping a bit here, which is okay for this one. All right, then I have a few examples to go through. I'm not sure I'll go through them all. I might just show you a couple and then do the more difficult ones so you can see how it's derived. Okay, so examples next. 4.7.